So just connecting to the previous part 2 for the support vector machine. So let's see how this KNN is interacting with the support vector machine. Uh, so in this one, you can see that in support vector machine and in the KNN, basically KNN means stands for kth nearest neighborhood, and basically it's a cluster approach. So it's like it doesn't like directly connected with that one, but let's see that how the author of this book has connected these two concepts together. And we can see here our default setup training for binary classification, and there is a two classification which is like falls in true or large or medium t-shirts. Weight and height are given as the two attributes or parameters, and then input we have this one with the d equal to 2, feature is n equal to 18, and class is y. And then we have like here I is 6, right? And then still we have the false answer. And okay, so to predict category level y of the new point x, we need to find nearest neighbor according to some distance metric. And after that one, we need to go for majority label. And to predict numeric value y for the new point x regression, we need to find the k nearest neighbors. Average values is suited with the neighbors. And if we change k, we may get different predictions. Yeah. So in this one, what is the the final verdict is, yeah. So if the k is 3, means the radius, if like for example is 3, or so what you get it. Okay, now here is k, the number of elements are 5 now, and then the star is not, it's a centroid basically, it's not like at the point, so you should not include the star in it, and also not the star, so the points are 3 here, and here 5 points, right? So by this way it gets longer. So what does nearest mean? We have to look in the nearby points, you can see that what are with the distance. So sometimes we use the Euclidean distances, sometimes we use Manhattan distances, and we have some Japanese name distances. There is a specific name for that one. Once I remind, I will let you know about that one. Yeah, so the distances are used over here, and it's the high school distances, which you already know about it, that how to find the distance between 2 points. Yeah, and the different distance produce different outcomes. We have it like k equal to 1 neighbors, and classifier decision boundary plot show that what class would be assigned at every point x, right? So we have point distance p2, and this one. So now see, you can see you can find the distances between different patterns, and based on that one we can have a decision that which cluster should be at what kind of shape it would be. Yeah, for non-numeric data, what are the distances? Yes, it's a very good question here. Hamming distance, like for example, Hamming distance is usually used like kind of exclusive, or you can say a number of characters that are different. Yeah. So for example, number of characters that are different. So what are the different characters like? On the first position, A is same, so it's not different. Second position is B, and another one is G, so this one is different. And then C and D is different. The third position one is different. Fourth position is same, DD, and then the fifth position EF is different. So three are different, right? So in the second example, in robot and bot, we have how many two two elements or two letters are different over here. Then we have a Jaccard distance as well, which is the union of A union B, A intersection B divided by the A union B absolute value, removing the negative values between the n-gram, and then so these are these are the different options which are available with us. Be aware, feature scaling affects the nearest neighbor. So feature scaling is also one of the technique which is used in the KNN. How to scale it, how to sometime rounding up, or our previous study we say that OLS regression was scale invariant. In Python we have the OLS as well. This function is existing. You can apply directly. Regularization was affected by the scale of the different feature. Even more of the concern with the KNN, note that we are using a distance measure like L2, which is affected dramatically by the feature scales. Yeah, what happens if we have many dimensions? Okay, like predict y equal to acceleration of an object being pushed by a remote control robot, right? And what if the features are like, x equal to mass and x static equal to force, and the color of the object, the temperature, x5 is air pressure, what operators are for the break fast, that is morning. Yeah. So in this one, as you add more irrelevant variable, the distance function, which are so-called KNN method, get dominated by the irrelevant dimension in x. So you must be very like very selective, okay? Or and there is a very a very important thing which is used in that one. Dimensionality reductions is used in that one. So some of dimension, they are not contributing in the labeling or in the prediction, so you have to remove that one, and you need to be selective by either majority voting method or by any method you choose it. So yeah, so curse of dimensionality, yes, add more dimension makes a lot of things weird and counter intuitive, right? For example, percentage of the volume of the d-dimensional sphere with radius r that lies beyond the p2 distance 0.9, and r from the center is like, for example, this one 63% at d, 100% and this one. So with enough dimension, most points are roughly equal distance. Yeah. For KNN, nearest neighbor becomes like very far apart and similar distances. Therefore, it's more unreliable predictions here. So, general advice. What's the general advice for us? Always worth trying K nearest neighbors, and it's so simple to code up that what's but it's worth it. Often works surprisingly well and is very widely used as a simple and reliable baseline. And you can say even with for really high dimensional data, it works very well as well. So this is the end of this chapter number 6 with the support vector machine and KNN together.